So, in the previous lecture, we have introduced an example from a multivariate nature. The iris dataset, a classic one where several outcome variables are recorded at the same time on the same units, in this case, iris flowers. In this lecture, we will start with longitudinal data, where also compound measurements are taken. That means the outcome is an outcome vector. And that refers to the fact that on the same unit we have more than one measurement. Only here, that measurement will be the same variable, the same outcome, growth in this case, in this example, but then measured at various points in time. Repeated measures means that the same outcome variable is measured on a unit, a person, or a cluster. But longitudinal data goes further than that and says, yes, it's the same outcome measured repeatedly over time, and time in itself is going to be of at least some scientific importance. So the setting here is we have 20 schoolgirls, and those schoolgirls are measured at a certain number of time points, 5 to be precise. The time points will be common to all of the schoolgirls, so that means we have a so-called balance design. Balance referring to the fact that indeed everybody has exactly the same time points. Not only that, the time points will also be nicely equally spaced. We have a group variable here, and that group variable refers to the body length of the mother. So the longitudinal independent replicate is actually the mother-child pair. It's not that the children are nested in mothers. We should not make that mistake. The children are actually unique to the mother. It's all girls, so there is no gender effect. But there is potentially an effect of mother group. And that mother group is defined as mother's body length, then discretized or trichotomized into 3 response categories. So here they are. The middle group is 155 to 164 centimeters inclusive. And then the other groups, 1 and 3, are the mothers that are shorter than that versus mothers that are taller than that. The groups are roughly of equal size. However, it's not possible to have exactly the same size because we have 20 mothers and that's not divisible by 3, but we come very close. So there are 6 and then 7 and another 7 children. It's not perfect balance, but we come close to it. And why is it important to emphasize and re-emphasize that? Well, under broad experimental design conditions, but I refer to other design courses, the closer one comes to balance, so all groups are of equal size, think of ANOVA applications, the higher the precision, so in other words, the higher the efficiency of the setting. So we should not be surprised to see 3 graphs. There is a graph for short mothers, for medium-sized mothers, and for tall mothers. And in each of those, you see a certain number of tracking. Tracking means that once you are in a certain profile, for example, high relative to the rest of the group, you sort of stay there. And of course, with some repeated measures, we would not expect that. With others, we do. Body length is something that is not crisscrossing all over the place. There may be a slight deviation from linearity, of course, especially because we would anticipate that growth over a lifetime looks more like an asymptotic behavior, looks more like an S shape, so to speak. But over a sufficiently short amount of time, and we talk here of measurements between the ages of 6 and 10, we would expect a roughly linear profile. The deviations from that being measurement error, but also there could be growth retardation for pathological conditions. Somebody may develop or be born with a certain pathology, with a disease. There also may be issues of starvation or whatever, well, hopefully not, but that could create some deviations from linearity. And that's simply measurement error, although I would not expect measurement error to be now so dominant in growth profiles. The other thing what we see is, going from one graph to the next, that the lines in the short mother group really start in the lower left corner, But in the taller mother group, they actually already start with a leeway. They start a bit higher than the bottom line. Well, a brief comment: if you create graphs automatically, for example, in R or in SAS, many graphical packages will kind of maximize the use of the space available, which means that many graphs would start in the lower left corner and end up in the upper right corner for each of the three profiles. But that would mean that the y-axis is going to be different from graph to graph. So there is actually value in forcing the y-axis to be common in a case like this to the three graphs, and that may be a user-defined choice. Why? Because then at a glance you can compare the profiles and say, from one group to the next, I see an increase. Of course, the visible assessment of that increase doesn't mean at all that it's sufficiently established. In other words, in more statistical words, I cannot say it's significant until I've done a formal, correct statistical analysis. Another thing we may ask ourselves, but we may not see, is that whether or not the curves are slanting. In other words, it's possible that the average evolution in the short mothers is relatively flat, and in the tall mothers it's much more rapid. Of course, I'm exaggerating here, but even though you may try and measure that a little bit, it's pretty hard to see on a graph. So, that brings me to the next example, which is a third type of example of cluster data. Here we have data on 102 lizard animals. And lizards, as they grow, just like children, they get bigger, but also they develop more shells. And that's, of course, different with human beings. And we can count the shells as a size of, body length, but also body size, also maturation. So the question is this now different between male and female specimen? As such, if we count the number of shells, and we have two groups, males and females, we could think, oh, that is a two-sample problem. Maybe we can solve it with a t-test if we consider the dorsal shells as continuous. Or if you insist on their count nature, we can do a count regression, a Poisson regression. The thing is that there is a certain amount of clustering, and I will come to that in a minute. Moreover, if we look at the graphical exploration, we see, for example, that the male and the female averages are different, and that's the way a mathematician would look at them. The means are different, sure, within the sample, but there is a huge error bar. Or rather, there is it's not an error, there is actually spread in each of the two groups, because even among the males there are shorter and taller specimens, even among the females, same story. So at first sight, it looks like there is a pretty large amount of variability, telling us that we may need a pretty large sample size to overcome the noise and start to clearly see the signal. However, as I said, in this index plot it becomes clear there is clustering. In other words, for every vertical line, so I'm referring to all points that lie on the same vertical line, there is a single mother. So unlike in the previous example, where the mother-child combination was unique, for one mother there was one daughter, but here we have for every mother two, or sometimes one in the second one, or sometimes more offspring, specimen. Which means that there are 30 independent replicates, that's level 1, but the mothers, but level 2, there may be 2 or more replicates per mother, and that's level 2, the offspring or the little lizards. Okay, further, we note that within every mother, we can have a male and a female, or we can have just one, or we can have sometimes two offspring of the same gender, and you can try hard to find every time a male and a female, but that may not always work, and sometimes you can even have 3, etc. So the bottom line is that we also here have clustering or nesting. In the previous example with the schoolgirls, the unit was the mother-child combination. That was the first level. And then the replication was the repeated measures over time. Time is not present in the lizard example. Level 1 is the mother, and level 2 is the offspring within the mother. Of course, if I have a male and a female offspring, the male can be oldest, the female can be oldest, but sometimes even the number of offspring per mother is not the same. So this is a very unbalanced setting. It's very different from the previous setting, where every child, recall, nicely produces the same number of measurements at the ages of 6, 7, 8, 9, and 10 years. It's a clean, balanced design. By nature, in the current problem, that's not possible. Is that a problem? No. If we build a model that can take this properly into account, it's not a problem. So what is the advantage of this design? What is the rationale for choosing this design? Well, even though the overall comparison here showed that there is a bit of a difference between males and females and a lot of noise around that, if we look throughout the board, we will often see a clear difference within every mother, but of course there also is mother-to-mother variability. So to cut a long story short, and that will then come back in the next part of the course, what we want to do is separate the within and the between mother variability so that we can really see the difference between the genders more optimally. And one lesson to learn, and it's too early to give the arguments, but when time comes, one lesson to learn is, well, within unit comparisons will be much more efficient than between group comparisons. We kind of know that from the pair t-test, right? So something similar to the pair t-test will be done here. Well, by the way, is this not a pair t-test? Well, that's a good question. It would be if for every mother you had exactly a male and a female offspring. So 2 for all, and then one of each gender. But that would be then again a clean design. We don't have that, so we cannot do that test. Okay, so in summary, we see a lot of between mother variability. We do see that males seem to be higher or larger in number of dorsal shells than females, but that needs to be separated. These two things need to be separated. We have cluster data, which is kind of an amorphic, unstructured version of longitudinal data. Rather, it's a hierarchy in the data set, level 1 mother, level 2 the lizard offspring, but without a clear further organization of the measurements. We simply cannot do that. Okay, and then the third example of cluster data is from an area called developmental toxicity studies. And in developmental toxicity studies, what we want to know is during pregnancy, if a pregnant mother is exposed to toxic agents, what is the impact, the adverse effect on the growth and even the survival of the child? So, of course, this is what we want to know in an industrial society. We use chemical compounds all the time. And we can say we can take it even further because we've grown very conscious towards pollution, environmental pollution, and a number of issues around that are now well known. They're often at the forefront of the news. But also, when your plane is to depart from a very cold environment where it has been snowing and freezing, etc., it's not very healthy to leave the plane, to make the plane leave just like that. It should be de-iced before taking off. And that's what we call, or the compound to do that is what we call ethylene glycol. That same ethylene glycol you may find, for example, in your fridge or your freezer because it's a liquid that helps to extract the heat from the box so that it gets colder, cool enough for the fridge and starts freezing for the freezer. That's all nice and well. These are very valuable industrial and modern society applications, but these compounds are not innocent. And of course, we are not going to try them out on pregnant women. So therefore, we are going to expose for example, rodents, rats, mice, rabbits, whatever animal model is most useful for this. Of course, by having good experimental design and analysis tools in place, we also hope to reduce the number of animals that we need for that. So, we will be dealing here with a segment 2 study, which is a teratology study, and that has to do with what happens during the period of major organogenesis. So when the organs are created, formed, when the organs take shape. And we also know that in human pregnancies, the second half of the first semester, or first trimester, sorry, is actually a crucial one. Many people say it's common wisdom. Once you're past the first trimester, things are more secure. Segment 1 studies, just for information, we will not do anything with it. That is fertility studies, male and female fertility. And segment 3 studies is what happens later in gestation. So, when we talk for human beings of pretty much a good part of the first trimester, for rats and mice in particular, it's a much shorter and much earlier period. It may be, for example, for rats, between 6 and 15 days into development. Okay, so we do an experiment where we take a number, 20 to 30 pregnant dams for a given dose group, and then we expose the mother to a certain compound at a certain dose level, and we examine the fetuses for malformations or whatever you're interested in. Good. Of course, that's not enough. That would be just one dose, so we do 3 to 4 dose groups going from a placebo control dose, no dose in fact, to a highest dose, and in between we usually go in multiplicative steps, so we double every time the dose. Good. So, just to fix ideas, we have here implanted fetuses, and these fetuses are, in human beings, of course, we would typically have one fetus, or occasionally there can be 2 or 3, but with mice, you're going to have something between 2 and 16 typically. The average is around 12, so that's why we see a whole line of fetuses in the uterus. Good. The outcomes of interest first, what happens first is death or resorption. Death is clear. The fetus is there, but it's dead. Resort means it's actually not visible anymore except for a dark spot in the uterus line showing that there once was a fetus, and that's in a way even more problematic because the problem happened earlier. And then there are the viable fetuses, and the viable fetuses can be examined for a number of things like visceral malformation, and that is in the organs, the heart, the brain, the lungs. Skeletal malformation is pretty clear, the bone system. And external is a malformation visible by a naked eye. Of course, they're not exclusive, so it means it's perfectly possible that a fetus has one of them, but also 2 or even all 3. And another variable of interest is weight, not because weight as such is an adverse event, but the lower the birth weight, the more the fetus may be prone to other diseases because of lack of resistance, lack of strength, etc. So weight loss is a risk factor. Okay, good. The data structure. It's important that we draw a line here where I drew it. So we have a single dam. And of course, you know that in the actual experiment, we have a number of dams per dose groups, then we have a number of dose groups altogether, so we may have in an experiment something like 100 of those dams. That's the typical size in the data sets that we will be analyzing. Okay, then the implants, of course, as I said, it varies between 2 and 16, with 2 relatively uncommon, 16 relatively uncommon, but the number of implants is variable from mother to mother. But it's a pre-randomization or pre-experimental variable. That means we have no control over it. We just select a number of dams, pregnant dams, into our experiment, and they happen to have a number of fetuses. Then we apply the dose here, and then we have the other information, which is post-randomization. I mean, you can imagine that MI which of course is equal to Ni plus Ri, well, that division is going to be different from group to group, from dam to dam. So there are Ni viable fetuses. You would expect that Ni is closer to M in the placebo group or in the low dose group, and maybe Ri is closer to M in the very high dose groups when they basically all die or get resorbed. So the split of M in N and R is going to be in itself very useful. It gives us information about the dose-response relationship. Likewise, if we further examine the viable fetuses, we will see that some have malformation type 1, some 2, some 3, some all of them. So in general, we could think of K malformations that will be examined. And then weight is, of course, also to be examined. Now, before we start panicking, because it's such a complicated design, and it is, we should realize that we are not obliged to, from day one, start to analyze the entire data structure. We can formulate meaningful sub-questions and simplify the development a little bit. So, what is the question? The dose-response relationship, I already mentioned that. What is, for example, the fraction of viable fetuses as a function of dose? A function of dose is of interest. We may test for the dose effect. So that function may contain parameters, but if all the parameters associated with dose are close to 0, we may not have a dose-response relationship. It may be trivial. So then that would be good, because it would mean that the compound is actually relatively safe. We could estimate the dose effect. And a side product, an important derived product, but important for practice, is the so-called benchmark dose. It has a lot of different names: the effective dose, virtually safe dose, lethal dose, depending on the concept. But it usually refers to, like, what dose do we need to apply to come to, let's say, 20 or 10 or 50 or 90% response. In other words, the lethal dose is, what dose do I need to apply to kill 50% of the fetuses, 90% the same. But here we're interested in safe doses. That is, till what dose can I go to make sure that applying using the chemical compound has no risk? Now the answer there is very simple: 0, no dose, because that's the only one that is guaranteed to provide no extra risk, right? However, that would mean that industrial society stops. All the doses are equal to 0. In other words, there's nothing we can use. So we usually define that as what dose can we allow so that the number of cases that we add, in addition to what is already happening in nature, is just 1 per 10,000. In other words, even in safe environments, there would occasionally be people who are born with skeletal malformations, or rats that are born with skeletal malformation, not because they were exposed to a dose, just because of bad luck, genetic makeup. So the question is, for every 10,000 cases that happen naturally, and that can take a very long time, fortunately, we are prepared to take 1 additional case coming from industrial society. That would be pretty much the choice. So that will be then a final product for which you have to estimate the dose-response relationship carefully. Okay, so what are the issues? Of course, there is the litter effect. All fetuses coming from the same mother will potentially be correlated, like the repeated measures we have before, like sepal length and petal length in the iris data set and whatnot. Next, the weight outcome and the other outcomes are not of the same data type. The weights are binary, the other ones are, the weight is continuous, not binary, but the other ones are binary. And then about the binary indicators, what is of interest now? Each one of them separately, skeletal, visceral, external. Or should we build a model for the 3 together, a trivariate model, trivariate cluster 10? Hey, but that's multivariate again, true? So we have a multivariate hierarchical data problem. Or a collapsed outcome could sometimes be of interest, that is, either one or the other or the third or a combination thereof occurs. And then another problem that we will not address here is, okay, when we have now estimated our parameters, how should we now go from the animal model to the human model? Is it the fetus which is of interest, or is it the litter as a whole? We might say the litter as a whole is a model for human pregnancy, but you may also say the mouse or the rat fetus is a model for the human fetus. So that is not entirely clear. What model are we going to use? What estimation families are we going to use, etc. Okay, this is the area. Let's now get more concrete and see that we can conduct such an experiment. And I'm referring to experiments done by the Research Triangle Institute, RTI, in Cary, North Carolina, US, under the auspices of the US National Toxicology Program. Okay, so we have, for example, ethylene glycol, but I will also be using data from 2 other studies, DHP DIME, and there are actually five altogether in this batch of studies. So ethylene glycol was already mentioned. For those people who want to see the chemical formula, here it is, but of course that's nothing to learn by heart. It's a workhorse. It does do a lot of different things. I already referred to a de-icer on the one hand. It's also an antifreeze in cooling systems. For example, the freezer and the fridge, but also heating systems, for example, it's used, and so on. It's a softening agent in cellophane, otherwise cellophane would be rock hard. It's a way to make it soft, what it's supposed to be, etc. So as I said, it serves a lot of purposes. However, there is that hazard, especially if you ingest it, and of course, especially during pregnancy. Now, if a plane is de-iced, you may wonder, hey, that's never done by pregnant women, right? No, it's not done by pregnant women. That's illegal in most countries. But of course, if you de-ice a plane on the tarmac, some of the ethylene glycol will dissipate, will disappear in the earth, will vaporize, and will just enter the environment. And then the question is, what is the risk coming from that exposure? So, okay, let me briefly run over the EG study in mice. We have, as I said, time-pregnant mice, so that means we exactly know in what day of their pregnancy they are. We look during days 8 through 15, more or less coherent with the graph I showed earlier, and the doses here are up to 3,000 milligram per kilogram per day, ranging from 0 to 3,000, and then, as I said, with intermediate doses, half of that and 1/4 of that. Okay, so in each one we have a number of replicates, and each of those 4 doses then produce a piece of information. Such a piece of information can be the proportion of fetuses with one or other malformation. So, for example, if you look at the top panel, and it's there also for the 2 other studies, DHP and DIME, but also for 2 more, TGDM and theophylline. You see the dose levels. You see the number of dams with implants, 25, 24, 23, 23. All of them except one have viable fetuses, and this is the number of live fetuses. And that column now, the last one that I circled, you see come down as you go from top to bottom. So the litter size indeed varies from nearly 12 to 9.8. So it decreases, and you may say not dramatically. No, not dramatically, but it does. It's already different for DHP and DIME. Whereas for TGDM and theophylline, you see very, very low decline. So it stays more or less what it was. Okay, then if we go back up, we see the proportion of external malformation going from 0 to 7%. So in the 3,000 milligram per kilogram per day dose group, 7% of the fetuses do have external malformation. Skeletal malformation, and that's of course very interesting to compare, goes all the way to more than 50%. If I go to DHP, all three of them show coherently a large increase. And in DIME, it's a little less severe in visceral malformation, but look at external and especially skeletal malformation. So the picture is different from compound to compound. Theophylline, as a statistician, you may say, that's bad news because the numbers are so small, probability is all close to zero, that may be difficult to estimate. And you would be right, of course. Of course, for the public and for people working with these compounds, it's actually good news because it shows that there are very low frequencies. Okay. So if we focus further on the EG study and add one more thing, the weight variable, then you see that the weight variable here has an average of nearly 1 in the lowest dose group, and then only 0.70 in the highest dose group. So you do see a decrease in the weight group. Okay. So then we have the percentages that come down. We saw that before. Huh? Good. The number of implants. The number of implants, remember, that's MI. But as I said before, unlike in the growth data sets, the schoolgirls data set, where there is nothing to be said about it other than that every child has 5 measurements. That's not something to be totally surprised about. No, it's you as an experimenter who decide that, but here it's nature who decided. So we may say in ethylene glycol, we have 0 mothers with 0 implants. We have 1 mother with 19 implants, but the bulk is really sitting here between 12 and 15, 16. The distribution is the same in every column. That's what you would expect. Why? Well, once again, it's the same species, and all of this is pre-randomization, pre-experiment. It doesn't matter that later you're going to give DHP or DIME or theophylline, etc. You just have a number of mothers that are pregnant, and you typically will see the same distribution. For when it's needed, you can actually pull those data and estimate from there the empirical distribution of the number of implants. Okay. For some of the variables here, we have created relative frequency, so that would say that for lower dose groups, there is little or no malformation, for example, and then it goes up, and in the end, it would go to 100%, a bit like a growth curve or an S-shape, the S-shape typical for the logistic or the probit function. And yes, these are binary data. We would not be surprised to see that. The fact that we see an S-shape is not so surprising, and it's not really a subject of study. The subject of study is what do we do with that S-shape relative to other S-shapes? In other words, do they coincide? And that would mean that there is no effect of dose, or is there a clear distinction from one dose group to the next, like we see here, etc. Okay, and then if we look here, we see that for every dose group, the number of malformations or the malformation rate is plotted per liter. Well, of course, for those equal to 0, you see only 1 point because all the points coincide and are 0 or very close to 0. For the highest dose group, you start already with a relatively high mean compared with the other dose groups, and then there is more variability. So we do seem to see at the same time heteroskedasticity, which means for every dose group, there is potentially a different variance. And we also see an overall increase. So if we eyeball, we would kind of get a relationship like this or like this. You can actually draw it through the means because the means are indicated with crosses. Just for the sake of information, there is also a study in rats where we have doses in terms of gram per kilogram per day. Huh? We don't talk about milligram right now, but rather grams. And then we have a very similar experiment with a number of DAMs for each one of those groups, going from the lowest dose to the highest dose. And also here you see the liter size coming down, and you see malformation rates that are relatively similar to the one we had in ethylene glycol in mice, but it's not necessary. There's no reason why it should be exactly the same. Well, just imagine, which is not the case, but just imagine that one of the two species would be totally immune for the compound. You would see no effect in one. And if the other one would be very susceptible to it, and that can well be, not so much usually in rats and mice, because we tend to be remarkably similar with rats and mice, but it is different for other animals, of course. So what is toxic for one may be completely non-toxic for the others, etc. You don't a priori expect the same. Here we have an interesting additional variable. That's the empirical correlation per dose group between the outcome variable weight and the outcome variable malformation. One is continuous, one is binary, but we can still calculate the Pearson correlation, and we do see while weight and malformation indicators are sort of independent in control circumstances or close to it, for the highest dose group, it is considerably different indeed. And then also here we see some empirical evidence about the evolution. And so if we nicely connect what I'm doing here, the averages, you see the empirical dose-response relationship. But again, also here, we do see a certain amount of heteroskedasticity. We should not deduce from there that whatever model we consider, it's going to be more complicated than we thought, because some models may well have built that in, of course. And the next graph is one that goes down on average, because that's the weight graph. There we have the weight of the animals, which gradually decreases as the dose group increases. All right. And then a final example, the heat shock data set. Well, in the heat shock data set, we have a data set similar to the previous one, yet it's a bit of a special nature, because we expose the fetuses, the rats or the mice or whatever animal you're considering, explanted from the uterus, so taken out of the uterus, and you expose it in this case to so-called heat stress. So during a certain amount of time, from 5 to 60 minutes, and at a certain degree, they are exposed to, and literally degree, at 3 to 5 centigrades above normal body temperature, they are exposed to increased temperatures, body temperatures, water temperatures in this case. And then later, they are examined for effects on all sorts of body length and body measurement outcomes. It's an alternative segment to study, one that is not really used so much, but it allows us to do something very different from the previous one, that is work with individual level exposures rather than group level exposures. Okay, good. So the design is we have 327 embryos, and like is not uncommon in studies of this type, the experiment itself provokes stress, so 50 do not survive the heat stress, which in itself, it's not a failure of the experiment, it's an important outcome, it's an important piece of information. 277 have complete data. And I will come to that. We would like to verify Haber's law, which is not the duration of the exposure is important in its own right, not the exposure level, so the temperature is important in its own right, it's rather the combination of the two. And that would mean that 2 minutes at 30 degrees or 4 minutes at, the other way around of course, 30 minutes at 2 degrees or 15 minutes at 4 degrees would have the same effect. Now, that's not something we start from. It's a hypothesis we start from. We don't know it. It may well be incorrect. It may well be false. It might have to be falsified. And of course, you could imagine that the very extreme situations would really create some frowning. If you say a very short exposure, but to a very elevated temperature is the same as like the moderately long at a moderate temperature exposure, no, because that very high exposure may burn the fetus alive, of course. if you wait for too long and you have an elevation of 0.1 centigrade, that's a very low elevation, but for a long time there may be nothing happening, but then because of that exposure in the first place, even if it would be at normal temperature, you would start to see certain effects. So Haber's law is a bit shaky from the beginning. Okay, and then we have a number of binary outcomes: midbrain, forebrain, olfactory system, branchial bars, which are all body and system parts. And the question is, are they affected, yes or no? And then there's a number of continuous outcomes: the size of the yolk sac, the crown rump length, the head circumference, etc. Okay, and then here we have not the data, but the design behind the data. So we have temperature, 0 elevation, 37 degrees, a bit like human beings. 42 is 5 degrees exposure, and I hope you realize now that 5 degrees is not like, hey, that's a low temperature. No, 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 no. It's 5 degrees above normal temperature. And you and I can stand pretty high external temperatures, but if your body temperature is 42 degrees, you're extremely sick. And we do react to the smallest change in body temperature. It's something for a healthy human being that's supposed to be pretty constant and vary only a few cents or a few tenths of a centigrade. 1 degree from 37 to 38, you don't feel well anymore. You may not feel terribly sick, but you don't feel well anymore. And then the duration goes from 5 to 60. Now, over that time frame, if you're exposed at 37 degrees, which is normal, for 5 minutes or for 10 minutes or for 20 minutes, I would not expect a difference. So this is why we have to do something special with that variable dur temp, as we're going to, or and post-dur, as we're going to create it. So the variable post-dur, a bit later, will capture that. And again, we have a distribution of the cluster sizes. It may not coincide exactly with what we have seen before, because here we select like individual fetuses. The individual fetuses belong to the same mother, but it's a different story where you say, okay, let's have the mother, examine that mother's uterus line and record them as viable and then non-viable, dead or resorbed. Okay, and this is the data. So, and in the plane, in the XY plane, we have again temperature and duration. But above every one of those points, there is a kind of a spear form or a flower growing, and the length of the stem of that flower corresponds to the number of replicates we have there. Now, it's immediately clear that this is absolutely not uniform. And it may be better to have something uniform or something capitalizing much more on the counters, on the corners. But then for the high dose groups, so high temperature and high duration, high temperature level and high duration of exposure to that temperature, we may actually not have enough viable fetuses. So it's also poor man's choice, so to speak. Okay. With that in mind, we can now turn to Haber's law. As I said, there we have, the law would say that this is true. We have a dose-response relationship, the function P of D and T, but note, D is not duration and T is not temperature. D is temperature because that's the dose. D is dose, and dose is temperature in degrees Celsius. And then T is time. So that is the duration. It's a bit confusing because the D variable has a T companion and the T variable has a D companion. So keep that in mind. Okay, and then what people have done before is include dur temp. Dur temp is, again, the duration, just like that. So T is the duration, but T multiplied or modified by delta is cancelled if you have an elevation of 0 degrees, so no elevation, but it remains in full action otherwise. So it's actually a main effect of temperature, except that we correct for this specific boundary issue. Okay, now it's open to criticism. You can say, hey, but that's the main effect of T. of time, duration. What about the main effect of the other variable? Because there is not just time, there is also temperature, the actual dose level. True, you could consider one, the other interactions, you could have powers, etc. But they use this model, and we use this model because it already does the trick. If you're convinced that there is a problem, there is a problem, and this analysis actually will show it. What are the challenges in model development? Well, also here, the hierarchical structure. So the thing is, it's a little easier than before because we can do the exposure at the individual level, but this does not take away the litter effect. It's not because, and that's often misunderstood, it's not because you have individual exposures that there's no cluster level exposure. It really is at the individual fetus, yet they have the same, or not the same, they have similar compositions, genetic compositions, they come from the same mother, so there will be environmental and biological genetic reasons why they behave more similarly. Okay, as we said, the litter size may be related to the outcomes among the live fetuses. So the more live fetuses we have, the larger the litter size may be, and that's sometimes of an issue. We do need to take that into account. Multivariate nature of the data is also there. There may be correlations between the various fetal endpoints that you need to consider. Yolk sac, crown rump length, etc. They're different variables, so there is also there, if I cycle back, a multivariate nature with here, and the list is longer than what I'm showing here, 4 binary variables, 3 continuous variables. So altogether we have now 7 variables, so we have a 7-variate problem embedded in this not too complicated but still hierarchical structure. Okay, and that brings me to the end of chapter 2. Chapter 3 will be some background in terms of notation, conventions about data, structures, etc. So that one will be pretty much real examples free. It's the mathematical background that we need for the multivariate part on the one hand and for the longitudinal part on the other hand. And then we will start modeling in the next part, which will be the ensuing chapters.